So we have got this spatial discretization that was optimized for capturing wave numbers properly in your solution, and we have got this time discretization, and we will see that that is all that we need. Although we would expect, say, one might expect, okay, our wave equation is second order because there is a Laplacian, but we will not be solving the wave equation directly. We will solve the first order linearized Euler equation, and so we will talk about that. And we have already shown in the previous lecture before we got into CA that linearized Euler equations captures all of the acoustics that we want to study. So I will remind you of this linearized Euler equations that we had. So these are the equations that we had, and we took some pains to derive these. Now that pain should bear some gain. So we had equations like this, where the first one, so our assumptions were of this form, or maybe I'll ask you the assumptions. So what were the assumptions in deriving this? Not uniform, because we are still taking del dot u0, so it's not uniform really as yet. So linearized. Anything else? Base flow is steady, yes, okay. Base flow satisfies an Navier-Stokes equation. No, it could be unsteady also. You can have an unsteady solution to the Navier-Stokes equation, and that might be chosen as the base flow. Here we are not doing that. Anything else? Nothing, right? So we kept this very general. Then we came around and using Courvoisier, we added some additional assumptions. So what additional things did we do? Not really. Uniform base flow. Inviscid, and so no molecular diffusion processes. That is inviscid and non-conducting. Because this course is running in the aerodynamics, space engineering department, you are all okay with inviscid, okay, because we have seen the power of inviscid for our aerodynamics, and so you are all probably not questioning about this part. The uniform base flow is definitely not the most general that you can have. So Courvoisier had to bring in the uniform base flow to show that what is acoustics, to decompose or decouple all those three components of fluctuation, linearized fluctuations, to show what is acoustic, which is the irrotational and isentropic part of the fluctuations. So we will now specialize these equations to these, and we will do one other thing. The one other thing is that we will choose our x, y, and say possibly z. We will choose our axis to be along the u0 direction. So the u0 vector, whatever it is, so we will choose the x axis to be along the direction, so that my u0 becomes simply scalar u0 I and nothing in the j and k direction. Just a convenience for us to, and we can do that anytime because we are not allowing for the base flow to change in time. So of course for a particular problem there will be a uniform base flow and that will be steady, and so it will, we can always choose our x axis to be aligned with that x. So with that, and of course with the inviscid and non-conducting thing, you already showed that energy equation we had written in terms of the pressure. That was your quiz problem, that dp dt, if I remember correctly, plus gamma p del dot u is equal to 0 is another variant of the energy equation. So what were the assumptions for this? I didn't ask you that, but what were the assumptions for this? What do you think are the assumptions looking at it? Remember, isentropic is not required by Courvoisier. So just like irrotationality is not required by Kovácsny. So these are not assumptions that you have to make. It turns out that the acoustics are living in a world of its own, which is isentropic and irrotation. But that's the beauty of this Kovácsny. So what were the assumptions that went into this? What does it look like? If you look at the energy equation in terms of entropy, what must have been thrown out coming from 9C to this? Viscosity and conductivity, right? Though those must have gone out of the place. So our entire right hand side would have been 0, and the left hand side you can massage in terms of pressure using the. So we'll see how to model the source term in our numerical calculation. And we can massage. So I invite you to do that. So you can massage the energy equation now in this term, in this form, and we can linearize that. Okay. So if you do all that things, that is, first of all, you take u0 to be uniform, and you choose your x-axis to be in that direction, and you write your energy equation in terms of pressure of this form. And after you do the linearization of this was your quiz problem, and it was this thing. So that was your linearized energy equation, right? So you do that, and then you can write the linearized Euler, because it is no molecular diffusion problem. That is the essence of Euler from Navier-Stokes. And with a uniform base flow in the direction of x, you end up with these equations that are given in Tam's book. So pretty much any paper you take for LE, they will have equations of this form. So again, our solution variables here notice that we are not trying to do any further manipulation of these equations in terms of, okay, take the divergence of this, take the time derivative of that, and nothing of that. We are going with the original equations, and we are just writing them in a vector form. So the capital U is our solution variable. We want to know what is the rho, u, v, and p at any instant of time and at any location in space, and that is governed by this top equation, where E and F are the quantities that have to be taken the x and y derivatives of, and again these are vector quantities. H is a source that we leave in our equation, and we can use that if required. For your homework and for our purpose of this course, we will not be touching H. So we'll only have an initial condition that is going to excite some waves. So again, I invite you to do the little mathematical manipulation that is required to go from the equations that you have already derived to reach here. Okay, be comfortable with these equations. This is the linearized Euler equation that we want to solve. So addition is 2-dimensional. Okay. Just to keep your computational effort low, although we recognize that 2D acoustics is not the most general case, 3D would have been better, but 3D is one extra dimension, and which will take much longer for you to simulate. So to start off by in trying to understand the performance of your numerical schemes, which is the point of this exercise, it is better to have a 2D problem. You can debug and play around easier. Okay. So how do you solve this? Given a particular initial condition, that is knowing what is rho, u, v, and p at everywhere in your flow domain at t is equal to 0. How do you solve this? We already know. We know how to do del del x. Del del y is of course doing this in the vertical direction with the same thing, same exact approach. And once we get that, we will take them to the right hand side. That will be our f of u, and we will take the times optimized time marching scheme to take it to the next step. Boundary conditions. A PD is not defined without the boundary conditions. So we have to worry about our boundary conditions. Okay. So our effort, we will not try to derive or go through the exact footsteps of Tam's derivation in trying to understand where do these boundary conditions come from. I'm going to give you some intuition to help you not be too uncomfortable with the results. Okay, otherwise we will not go, because as you can follow in the textbook, it is highly technical, and we will not get into those things because we've got other things to talk about in the course on aeroacoustics. So this is the problem that we want to solve. the simplest of problems that we can think of, that there is some domain, and because we are our schemes are derived for a uniform Cartesian grid. So remember, our schemes are derived for a uniform mesh in X, 7-point scheme, uniform delta X. So the simplest of problems that we can deal with, the geometry that we can deal with, is an open problem, open boundaries. So no walls like this in the room, it's all open ground and it's 2D. So this is our X direction, this is the Y direction, and we cannot also, as of now, right now, we will start doing that later, we cannot deal with any complex solid structures in the midst of this problem. Okay, so but you can do that later when you account for wall boundary conditions. So you can have a, suppose for example you want to understand how does sound propagate, say an helicopter is flying, how does that sound propagate in a city environment where there are so many tall towers, how does the sound propagate, does a bank of suppose if there is a bank of buildings, will that cut down the sound that will be reaching here? Okay. Or maybe a very practical problem is that these you have seen these acoustic barriers on highways. Okay. So you can simulate some of that. Okay. How much of the sound will actually escape around or over the acoustic barrier? So you can try to do something like that. We will not get into those details as of now. So we will assume that somehow some acoustic disturbance, so some general disturbance. So disturbance in the sense that some initial value of rho, u, v and p all, so this remember is capital U, at t is equal to 0 is specified. Okay. Somehow that happened. Somebody sneezed in the room, okay, and then kept quiet, or somebody clapped and then kept quiet. How will that sound propagate? Okay. So we will think of the simplest problem, and we'll take this problem of solving this, because again we know the analytical solution of it through time's hard work. Okay. It's not obvious, but it is possible to solve these things. So what do we expect to happen? Can you sketch what will the solution look like if I suppose there is a small location around the center of this domain, that's why I chose the domain to be centered around that point, is where somebody say sneezed, somebody said something. How do you expect the waves or the fluctuations to travel in time? Yeah, we have got a mean flow, there is a u0 which is flowing along the x direction. You are not thinking of Courvoisier. What did Courvoisier tell you? This fluctuation, that is my sneezing, is it all irrotational, is it all isentropic? I wouldn't be able to sneeze irrotationally. I will create these vortices. So there will be vortical disturbances, and if I am very charged up, there will be also some entropy that I will be generating. So there is some entropy and vorticity disturbance along with the acoustic. How will they travel? How do you know that they will travel? You know how the vorticity travels. Vorticity and yes, yes. So we saw that in Courvoisier's work. So this was Courvoisier's result, right? That vorticity is going as d0 d0 t is constant. That means it is materially convected by the base flow. So here the base flow is u0. So if there is some vorticity in this thing, that will be just preserved. It will not be growing wave. It will be just preserved and it will just be moving uniformly with the uniform velocity. Same for entropy. So after some time, they will now separate out. So this will be the vorticity and entropy component of that, because all that sneezing was at the locality. So the vorticity and entropy will be all together. Whatever the shape of that disturbance might be in space, they will go together because there is a u0 that is convecting them.
So what about the propagation outwards of sound?
We will do that. It's not done. So they'll separate out. So this one, notice again that the shape did not change, neither the size, but then there'll be the sound wave also. So the sound wave indeed will be convected so it will not be centered around the source, it would have gone out but also be moved with the speed of the base flow, and that is also apparent in the d0 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 to d0 t square in the wave operator. So there is a motion of that wave front that is implied there, and we studied a bit of that in our earlier analysis. So this is what we would expect, that whatever disturbance is there, in general disturbance will not be purely acoustic, and so we expect that there is some entropy and or rotationality which is just trying to go out, go towards the right as driven by the base flow, and there are acoustic waves. So this boundary is what is called an outflow boundary, because the flow is going out of this. So this is an outflow boundary, and through this boundary the only disturbance that can go out is the so through this boundary all these three disturbances have to be propagated out without reflection. This is not a real boundary, this is my artificial boundary, because I don't have the capacity to imagine a larger grid or to solve for a larger grid. You have to choose your domain based on your computational resources that you have, and it's always finite. So you will have a certain boundary to your computational domain through which should be transparent to these waves: acoustic, vertical and entropic. And the other three boundaries has to pass through only the acoustic wave. There is no entropy wave that can reach these guys, because you have chosen your x direction to be in the direction of the base flow, and so this vertical boundary is normal to that x direction and the flow is going out of that. And so the other three boundaries are what I call the radiating boundaries, and this is the outflow boundary. So the outflow boundary has to account for the base flow. Yes, that is what Kovasny has told us, right? I didn't draw that right. Yes, you are right. So this would have traveled further. Try to. This would move faster for subsonic flow. So like the speed of sound must be faster than the speed of the base flow. Yes, and you are going to solve for subsonic, supersonic. There might be other issues that will. So the radiating boundary is somewhat simpler because it has to account for only the acoustic waves to go out. The outflow boundary is a bit more challenging because it has to account for outflow, moving out of acoustic as well as the entropic and the rotational waves or vertical waves. Right now we are just again thinking of no other boundaries in our domain. The entire rest of the computational domain is all flow, and so there is no further boundaries to consider right now. But again, the textbook does solve for solid walls also, and you can implement that if you've got the time and play around with that. Okay. So we will have to formulate boundary conditions in these cases. Now I'll go back to the fundamental question of maybe challenging Mayank here, that he said that you've got everything that we need. Del x, del y, we can get that. So we can get del u del t. In our actual implementation, where does the boundary condition come in? If we don't have any other boundary in the domain, everywhere we know the del x of E and F are known at the current instant. We can find the del x of that, and then that becomes our f of u, which we can then integrate using the optimized scheme to get u at the next instant. So I will tweak that. All of you are along the right path. I'll just tweak that a bit. Okay. So what you are suggesting is that suppose we are here, okay, or maybe you are more familiar with the x direction. We are here. So suppose there are some points in my domain like this. So for now we will just take 5 points. I can't draw 7 points. So suppose these are my mesh. So this is the mesh. 5 points. I'm just drawing a patch of that mesh. So that mesh is there, and part of your next ungraded homework, you are also looking at forward and backward difference schemes. So you know how to evaluate the derivative here. Say at this point, you know how to evaluate the derivative at this point based on the known solution values at the other points in the x direction, right? So you know how to do that. Your central difference will end here. That is because it's a 5-point scheme. Your central difference will end here. But these two also you know how to evaluate. You will of course do a asymmetric stencil there. Then what's the issue? Where is the question of specifying something from outside the domain if this is all there in your toolkit already? I completely agree with you, and of course we will need the BC. I'm just trying to get to the physical explanation of why we need to have to specify BCs here. Okay, so the U naught is actually in the governing equations. So U naught is already in the governing equation. There are no other fluctuations. Nobody else is sneezing in this room. Only I am in the only. You guys are just listening, and I am the only one sneezing in this room. That's what I am solving. I'm not trying to solve for cases where people are sneezing outside the windows and I need no. I want a simplest problem. You still need to articulate that if I know the values of my initial condition at these 5 points, why do I still need to have a boundary condition? Because it is their derivative through the forward difference which will go to the solution for the next instant of time. So the initial condition is known everywhere, including at these 5 points.
Okay.
I can find using the forward difference scheme the del x at these 2 points. So that is del E del x is known. I find out del U del t and then you do a smart. So my rationale, again, it's probably a philosophical thing, so there can be multiple answers. My rationale is that the backward and forward schemes are inherently asymmetric, and so they are damping or growing solutions. They've got damping or growing solutions. And so unless you specify something else in the boundaries, those ones will kill you soon. Those ones will grow because there are the growing solutions to that scheme that we have not talked about that. So those growing solutions must be somehow tamped down, but not just clamped down to zero, because that will be like a wall. So you need to do something subtle to allow those growing solutions to go out and not make your rest of the solution bad. So that is my way. Again, you can all think of it in another way because it being a physics and maths question. So there are multiple ways of looking at it.